Okay, part 3 of the modern physics series, a little bit about special relativity. Now let's recall, regular relativity has to do with an object and another object and how they relate to each other based on their moving frames. So if I have a stationary object and I have an object moving towards it at 1 meter per second, it's going to be perceived by this object as moving at 1 meter per second. But if the two objects are moving towards each other, both at 1 meters per second, this object in this frame is going to see this object as moving 2 meters per second, because this object is appearing in its own frame as stationary. So as they move together, this object is moving now twice as fast, because we're going to add up these two velocities. It's likewise if we have both objects moving directly behind each other, or one object moving to the right, the other object moving to the right at 1 meters per second, they both appear to each other's frame of reference as being stationary, as not moving, because they're not moving further or closer relative to the other object. Well, that idea starts to get tricky when we think of how light moves. We know that light is the speed limit of the universe. So what if I had a car or a spaceship moving at the speed of light and it fires a death ray forward? Well, the spaceship is traveling forward and the light ray, or the death ray, travels again at the speed of light. Well, they're both going at the speed of light, so this thing wouldn't even travel off. Well, it still will travel. This is just when we get into the idea of special relativity. So special relativity states that the meaning all depends upon your reference. And Galileo postulated that no matter what frame of reference you're looking at it, the speed of light remains the same. So no matter what's going on around it, no matter what's moving, whether it's reference frame or observed frame or moving frame, speed of light is always consistent. So we have a very famous equation, and it relates the mass of an object and the energy of an object. And it relates it to the speed of light squared. So for a very, very small mass, we're going to have a very big energy. And this is the rest mass of an object. This is the rest energy of an object based on its mass. And then we could also go ahead and add the energy of its moving, energy if it's got a spring, energy if it's got some potential energy. But this is the very rest energy. This is the energy that if we were able to take all of the mass and convert it into energy, this is what we would have. So let's try out a practice question. If I had a uranium bomb and it had 0.895 grams, if we were able to convert all of that mass into energy, how much energy would we have? Go ahead, try it out, and we'll come back. Okay, so we're back. What do we do first? Always write out the equation. E equals mc squared. You guys knew it before even walking into this classroom, or before sitting down and opening this video. E equals mc squared. Then we're going to fill in our givens with correct units. Notice it's kilograms, meters, and seconds. Okay? So we had to convert grams into kilograms. That's why we got 10 to the negative 4 now. How much energy do we get? A whole lot. 8.1 times 10 to the 13th joules. So that's enough energy to blow up the entire Earth. Yeah, quite big. Okay. So here's our little boy, which is the type of bomb that we used ending the World War II. So this was one of the first couple nuclear bombs that we discovered. A little known fact, New York City uses 9.5 times 10 to the 14th joules of energy. So to have 8.1 at a very single point, you're going to get some really big damage. And here's Hiroshima from 80 kilometers away. All right, let's try another practice question. Oh, my bad. Before that, we're going to talk a little bit about universal mass units. Because when we speak into kilograms, kilograms is a very big unit. Even right now, you probably don't even know what a kilogram is related to. Maybe you see a car and that's a few kilograms. But when we convert something, all of its mass, into energy, we're not going to use kilograms. Instead, we're going to use universal mass units, also known as U. And 1 U, or 1 universal mass unit, is equal to 1/12 the mass of a carbon atom, a carbon-12 atom. So that would be an example of 1 proton, or 1 neutron. Each has a mass of U. So 1 U is equal to 9.31 times 10 to the second mega electron volts. And mega is 10 to the 6th. So that's a lot of energy right there. Now let's go into our practice question. Okay, so the energy required to separate the 3 protons and 4 neutrons in the lithium atom is 39.3 mega electron volts. So let's convert that into universal mass units. Go ahead. Okay, we're back. So recall, we're going to write out our equation. And this time we have a comparison. We know 1 universal mass unit is equal to 9.31 times 10 to the second mega electron volts. So we're going to plug in, and we're going to create a fraction. So we want to find our mega electron volts in terms of universal mass units. So we have our mega electron volts on the bottom and our universal mass units on the top. And when we cross multiply, things are going to cancel out. We're going to end up with 4.22 times 10 to the negative 2 universal mass units. And that's it. We're now done with the section on Introduction to Quantum Physics. Those are your 3 videos. Thank you guys for watching. And if you have any questions, don't forget, ask in class. Go online and get some clarifying points. And that's it. Thank you for watching.